Hello everyone. Uh, Today we will be discussing about the ensemble theory in statistical mechanics. So basically, there are ensemble, as I discussed earlier. Also, ensemble is nothing but a collection of large number of collection of identical systems. So basically, which are interacting. Okay. So first of all, the first ensemble comes in our mind is microcanonical ensemble. The key features of this microcanonical ensembles are the large number of identical systems. They will have constant energy, volume, and number of particles. So what does this mean? So this means that you will be having a large number of systems interacting within themselves, but they can't exchange energy or volume or any particles with surrounding. So this is kind of a closed system. You can take an example of a gas in a container where it is not able to, like we are constraining that it should not exchange any energy, or the volume should not change, or neither any particle should enter the container. So that is an example of a microcanonical ensemble. So, but the problem here with this microcanonical ensemble is that it is very difficult to make the energy constant. So basically, if the container contains the gas particles, so it is very difficult to make energy of these particles constant throughout the experiment. So this particular ensemble is not very practical. We will see a few applications of this particular ensemble. But the most important ensemble is our canonical ensemble, which has a large number of practical applications. Okay, so here what was the problem earlier? The problem was that we are not able to fix like it is very difficult to make energy constant, right? So what we will do, instead of making energy constant, we will make the temperature as a constant. So making temperature constant is okay. So it is practical. How we will use a heat bath to make the temperature constant. So basically, this is also an ensemble. So ensemble means it is again the large number of systems will be there, but the key feature is that the temperature, volume, and number of particles will remain constant. And this is the most practical system, as I told you earlier also. Now the third one is the grand canonical system. The key feature lies that that we can also exchange particles also. So then chemical potential will come into picture. This also has a limited applications, but we will be mostly focusing on canonical ensemble. So this is the introduction to this ensemble theory, and I will be discussing all these three in details. And most of our focus will be in canonical ensemble. So let's come to microcanonical ensemble. So where this energy, volume, and number of particles will remain same. So let us consider that you have energy levels, right? So let's suppose the number of accessible states, the energy states between energy E and E plus D. So basically this is E and E plus D. You have number of accessible state as omega of E for any microscopic system. Okay. So, since for a microscopic system, there will lie a large number of what we say, this energy levels. They will be densely packed, right? So in between this E and D, you will be having omega E number of accessible states. So now this omega of E will be proportional to this gap of this energy levels. So this width of that interval that is D, let's suppose this interval is D, right? And if you remove the proportionality constant, you will get omega of E is equal to rho E D, where this rho is nothing but the density of states. Okay, and this will be signifies that how densely your states are packed. Okay, in between these any two states, two levels, right? And this has a very interesting application. Now, let's suppose, see here what I am assuming is, so you have some energy level this, and uh, and the another level is E, and E plus DE. So what I'm assuming is, if I'm saying that omega of E, then omega of E is the quantity which is representing number of states, or basically accessible states, in between E and E plus D. Okay. Now I am defining another quantity. The quantity is phi of E. Okay. So how phi of E is defined is, so here are your phi of E means if you have energy level E, then all energy levels below this energy E. Okay. So all energy levels, or all states below energy level E. Okay. So that will be counted as my phi of E. That is my definition. Okay. So you must note these two definitions. Now, if I say uh, E plus D, so phi of E plus D, then you must note that I'm saying that all the states below phi plus DE energy level. Okay. I hope you got my point. Now I will be doing some mathematics with this. So this phi of E is the number of energy levels below E, and phi of E plus D is the number of energy levels below E plus D. Okay. I hope you got my point. So if I am saying that in between, how many states are there? In between this E plus D and E. So that will be just the subtraction of these two phi's, right? It's obvious thing. So now what I can do using the first principle of derivative, I can write this number of state accessible state at energy level E. So what I am saying is, this is number of states accessible at energy E. So the number of states accessible at energy E, I am defining as omega of E, and that will be equal to the derivative of number of states below E. Number of states available below E. And then the time step, the width of the step. Okay. So let's try to do a problem based on the same thing, where we have a 1D particle in a box, where the energies are given by n square pi square h ket square divided by 2ml square. You also knowing that this n can take values only 1, 2, 3, starting from 1 to 3, and all these values are positive. So here what we have to find is phi of E. What is phi of E? The number of states available below energy level E. So like you can count energy level E also, and below that energy level, how many states are there? So that is what phi of E is. And then omega of E is the number of states between E and E plus DE. Okay. So how to proceed for this question? Okay. So if you notice here in the energy expression, you can take the value of n square as 2 ml square En divided by pi square h ket square, right? Or this n, if you notice here, it will be proportional to e raised to power half. Okay, so what does this mean? So if you notice here, the energy level diagram for this 1D particle in a box, it will be something like this. Okay, so if you see here, it is n equal to 1, 2, 3, 4, 5, right? If I am asking phi E2, so that is the number of states below energy level E2. So how many states will be there? So 1, 2. So that is equal to 2. And if you notice, that is nothing but n. Okay. So this n will represent the number of states. So basically here, but a phi of E is nothing but n, the number of states below energy level E, and that is equal to under root of 2 ml square pi square h kit square and then e raised to power half. So here, if you notice, this phi of E is proportional to e raised to power half. So now it is very simple to calculate what we know as omega of E. Omega of E is what? The number of accessible states between E and E plus D. So that is nothing but, from our first principle calculation, that is partial derivative of this phi and then delta of E. So now if you differentiate this, then you will get the proportionality for omega of E as e raised to power minus half. Okay, so that is the proportionality, and you can find the proportionality constant also. So let's try to go for three-dimensional case. So here what we have in place of n square, you will be having nx square plus ny square plus nz square. That is the 3D particle in a box problem. Okay, and the rest of the things are same. So here what you have is, you can consider this n square as nx square plus ny square plus nz square, right? And this is the equation of a sphere, right? Here you can consider a equation of sphere, and since these nx, ny, and nz all are positive integers, so here what you will be considering is the first octant. And what you will consider a sphere, first octant sphere. Okay, so that is consider a sphere which is in only the first octant, and the radius of that sphere is r, and r for, so this belongs to for energy E, and this will belong to energy E plus BE. Okay, so that I can calculate phi of E and omega of E. Okay, so here if you see here, then what you will be finding is this nx square plus ny square plus nz square from this particular energy equation. Then you will find that this is nothing but 2 ml square E divided by pi square and h kit square. So n square here is proportional to this, right? So here what will be, how will you find the number of states? So here, whatever be the so basically if we want the number of states below energy level E, so basically this particular, the r radius sphere is the is corresponding to energy level E. So the number of states below this particular sphere will be given by the volume of sphere. Okay, so that will be equal to 1/8, because it is on the first octant, and then 4 by 3 pi r cube. It is a r cube, where r cube is nothing but this n square. Okay, so that will be equal to, if I substitute from this equation number 1, then what will I get? I will get 6 here, 8 2 are 6, 5 r cube. In place of r, I can put n square, and that will be 2 ml square pi square h cut square raised to power 3 by 2, and then e raised to power 3 by 2. So here, if you see the proportionality of phi on E, it is proportional to e raised to power 3 by 2. Okay, so this is nothing but the number of states. I am again pointing out this is number of states below energy level E. Now we can also find omega of E, which is the number of accessible states between E and E plus DE. So that will be derivative of phi with respect to E, and then delta E. So what that will be? So if you I'm just writing the proportionality constant, you can write for the whole term by yourself. So that will be nothing but e raised to power half. So this is how the number of states between E and E plus D will depend on energy. Okay. Now let's move to next problem, that is 1D harmonic oscillator. So in 1D harmonic oscillator, the energy of this oscillator is given by P square by 2m plus half m omega square x square. This is a well-known thing. Now, how do we represent a 1D harmonic oscillator in phase space coordinates? So what you can do, if you arrange this equation, then what you will get is P square divided by under root of 2me whole square, you can write this, and plus x square divided by what it will be 2e divided by m omega square, and then whole square, right? Is equal to 1. So if you notice here, this is nothing but equation of ellipse. So how this harmonic oscillator will look like in phase space is basically by ellipse, where this major axis A is given by along this, so that will be under root 2e by m omega square, and this minor axis B will be given by 2me. Okay, so that so what will be the number of states? So basically this particular ellipse will correspond to energy level E. Okay, so if I want ellipse of E plus D, you can also construct ellipse of E plus D also, right? So now I want the number of states below energy level E, that is phi of E. So what will be that? So that will be nothing but the area of ellipse. So what is the area of ellipse? It is nothing but pi times major axis into minor axis. That will be pi. Also, I must use 1 by h. So h is used for the what we say that this is to make this phi of E dimensional less quantity. Okay, since h has the this dimension of p into x. Okay, so to make this this whole number, because it is a number, at last it is a number of states. So to make this dimensional quantity, dimensionless quantity, so we will be dividing it by pi, h. So the value of A is 2e divided by m omega square, and the value of B is 2me. So if you solve this, then you will find that this phi is proportional to what? It is proportional to E. Okay, so the number of states below energy level E are directly proportional to E in case of 1D harmonic oscillator. So therefore, the number of states between energy level E and E plus D will be proportional to del phi by del E. So therefore, this here in this case, if you see, it is proportional to e raised to power 0. So what does this mean? That the number of energy levels between E and E plus DE is independent of energy. It is independent of energy. Independent of energy. So let's try to do another problem. So here, in case of the potential is given by k x raised to power 4. So if you notice in 1D harmonic oscillator, you have potential as some k x square, right? Half k x square or something like the dependency on x is x square, but here the dependency is up to x raised to power 4 in 1D case. Okay. So here in this case also, what will be the formula for energy? So the energy here will be p square divided by 2m plus k x raised to power 4. Now here, if you also plot the phase space for this will also look like a ellipse, but some sort of distorted ellipse. Okay, some sort of distorted ellipse. So how do I know all these values? So let's suppose this is 0. So this is the point. At this point, the value of p is 0. So what will be the value of x here? So from this equation, equation number 1, I can find the value of p at this point. So if I put the value of p here 0, then x will be, it will be e divided by k raised to power 1 by 4, right? And what will be the value here? This particular point. So this will be correspond to x equal to 0. So if I make x equal to 0, then I will get p is equal to 2me. So these are the two extreme points. Okay. So now here also the problem is very similar. So the number of states between energy level, below energy level E. So this particular whatever the shape I say, it is distorted ellipse. This corresponds to energy level E. Okay, this corresponds to this energy level E. So now this phi of E will be equal to the area of this ellipse. So I can write the area of ellipse as dp and dx. Okay. So this is a distorted ellipse. Or what I can do, so this is one case. Okay. So also I can write the same integral as the function of p and dx. So I hope, I think that you must be able to know that these two things are similar. So here, this is the case of double integral. This is a case of double integral. This is a case of single integral. Integral here with respect to x only, but I am making p as variable, and with respect to, this is with respect to p and x. So in the first case, what I am doing, is, so this is my ellipse, and I am finding the area of this ellipse by making small pieces whose length is dp and width is dx, and I will integrate throughout this space to get the total area of this. So this is case 1. Now also I can integrate the same area, or I can find the same area of this ellipse by making a strip such that of width dx, and I will integrate over this curve. So here I can explain it better. So this is dx with strip, and I will integrate from 0 to all the way up to this point, e by k raised to power 1 by 4. Okay, so that is a possible way of doing this. So here, if you from equation 1, let's try to find the value of p. So the value of p will be 2me 1 minus k x raised to power 4 divided by e. You can easily check this. I've just taken the energy common out and underscore. That's it. So now I will put the value of p here in this third equation. So phi of e will be given by, the integration will be, I'm integrating from 0 to e by k raised to power 1 by 4, and then there will be 1 by h p 1 minus k x raised to power 4 divided by e, and then dx. And dx. Here, if you notice that this is the area of only this first quadrant, so it should be multiplied with 4 to get all the areas. under this curve. So this is the expression for the number of states accessible below energy level E. Okay, so now all we have to do is just solve this integral. Okay, so what we can do, we can use the substitution that, let's suppose U is equal to K by E raised to power 1 by 4 times X. Substitution. Okay, so what does this mean? This means that du will be equal to K by E 1 divided by 4 times X. Okay, sorry, dx. So use this substitution here, then you will find phi of E is equal to 4 by h, and the integration limit will be, when x is 0, the u will be 0, and when x is E divided by K raised to power 1 by 4, then u will be 1. And then you can take 2me out, and what is left over here is 1 minus u raised to power 4, right? Yes. And then here what will be K, sorry, here it will be E divided by K raised to power 1 by 4 times du, the value of dx here from here. Dx is equal to E by K raised to power 1 by 4 du. Okay, so from here I'm just not trying to calculate under root 1 minus u raised to power 4. So basically let's try to simplify first this. So 4 under root 2m, and then h here K raised to power 1 by 4 and E raised to power half and 1 by 4, so that will be 3 by 4, and 0 to 1 integration of underscore u raised to power 4 du. So now here what I have done is I have just made the integral, this integral, independent of energy, independent of energy. And where, if you see here in this particular integral, it is dependent on energy. Integral, okay, integral is dependent on energy, so that I was not able to see the behavior of the number of states below E as a function of energy E. So what I have done is, using the suitable substitution, I have just made the integral independent of energy. Okay, so so from here, so I can easily see that this phi of E is directly proportional to E raised to power 3 by 4, and from this I can also check that this omega of E is directly proportional to E raised to power 1 by 4, right? Sorry, minus 1 by 4. Okay, so this is how you should approach this problem also. So this is, I think this much problems are enough for today. We will be meeting with the next topics tomorrow. Okay, thank you.